Hey guys, this is the pre-lab for the Incline Kinematics lab, where very much like with the Atwood machine, where we figured out what the acceleration was going to be with kinematics, and then with Fnet equals ma, we'll do the same thing with our inclines, which are supposed to be frictionless. So just a little bit of review from inclines from Fnet equals 0 and some kinematics review, and then we'll get into the Fnet equals ma stuff. So a 5 kilogram block is at rest on an incline of 30 degrees. Determine the force of friction necessary to keep the box at rest. So when I do my free body diagram, I should have weight going straight down. I should have friction opposing the motion. It's going to want to slide down, so friction should go up the incline, and I should have normal perpendicular. The trick with incline problems is that we take the entire free body diagram and we rotate it. So we're going to rotate it so that the normal is straight up, the friction is that way, and then at our angle is our weight, our mg. And I'll write this over here so we can see better. Maybe make this a little bit thicker for you. And then our angle, our 30, is this upper angle. And if you remember, I had you guys watch a video where I showed you how to do that multiple times, how to prove that this angle was the same as the angle of the incline. All right, so this is my adjacent side. This is going to be mg cosine of 30. This is my opposite side. This is going to be mg sine of 30. So down the incline, Fnet is equal to 0 because it is not moving. And so I'm going to have friction minus mg sine of 30 is equal to 0. So friction is going to be equal to mg sine of 30. And so this is 5 kilograms times 10 meters per second squared times sine of 30, which is 1/2, which is going to give me 25. All right, so we're going to change this a little bit, and we're going to get rid of the friction. We're going to say it's a frictionless incline. And the inclines that we're going to use in this lab are very low friction. So we're going to say that the friction is negligible. You can ignore it. All right, so suppose the box above, it's not in the incline, but it's frictionless. What would the acceleration be? All right, so in this case, my free body diagram is only going to have weight and normal. And this will be what it will be for the lab. You're going to do this for 3 different angles. So again, I'm going to rotate it. And I'm interested in this side of my triangle. So if that upper angle is 30 degrees, the part of the weight that's trying to go down the incline is still going to be mg sine of 30. Now my Fnet has changed. There's nothing to balance this weight. So it's going to be Fnet equals ma. I'm going to take the direction of the acceleration to be positive. In this case, it's going to be down the incline is positive. So I have mg sine of 30 is equal to ma. It turns out that the masses cancel out. And so I have 10 meters per second squared times sine of 30, which is 5. All right, what are the 3 equations for motion? So these are constant acceleration equations, if you remember. So it's x minus x naught is equal to v naught t plus 1/2 at squared. It's v equals v naught plus at. and it's b squared equals b naught squared plus 2a x minus x naught. So in any case we have constant acceleration, we can use these equations. And so a frictionless incline would be a case of this. So we're an Atwood machine because the acceleration is constant. All right, I'm going to clear the ink and scroll this up. All right, so a 10 kilogram box is on an incline of 37 degrees. If the incline is frictionless, how long will it take for the box to slide to the bottom? The incline is 20 meters long. So what we're doing is we're reviewing what we did with Fnet equals 0. We're reviewing what we did with kinematics, and this is going to allow us, when we do the lab, to have an experimental acceleration and a theoretical acceleration using the second law and using kinematics. So if my box is here, my only forces are mg and n. I'm going to rotate it again. And again, this is going to be mg times sine of the angle. And that's always going to be the component of the weight that's down the incline, always. All right, so I'm going to do Fnet equals 0. I'm sorry, Fnet equals ma. I'm going to take the direction down the incline to be positive. That's going to be my positive direction. So I'm going to have mg sine of 37 equals ma. And so a is going to be equal to g sine of 37. So 10 times sine of 37. This is going to give me an acceleration of 6. All right, so I want to know how long is it going to take to go down 20 meters. That's a far distance. Our tracks are only 1 meter long. I want to make a chart. My b initial is 0. That's going to be the same thing as it's going to be in the lab. You're going to release the cart from rest. I don't care what my final velocity is, but it gets a spot in here. My acceleration is 6. And the distance that it's going down this very long incline is 20 meters. And then I have my time. So if I look at my x minus x naught equals v naught t plus 1/2 at squared, that cancels out. I'm going to multiply by 2, divide by a, and square root. And so I have 2 times 20 meters divided by 6 meters per second. So 40 divided by 6 square rooted is 2.6 seconds. Right. I'm going to put the ink and scroll up. All right, number 5, we have friction. This is much more complicated. With the friction one, we have a 25 kilogram mass on a 40-degree incline that's 20 meters long. I know what my coefficient of sliding friction is 0.25. I want to know how long it's going to take. So this is 40. Now I have mg going down, I have friction going up, and I have normal going perpendicular to the surface. That's hard to see, so let me do it over here. So mg going down, friction going up, normal going perpendicular. I'm going to rotate it. And this will be the longest of our problems. And then since my angle's up here, that angle, this is mg sine of 40, and this is mg cosine 40. So perpendicular to the incline, I still have Fnet equals 0. And so I can take my up minus my down, which means I have n minus mg cosine 40. So n is going to be equal to mg cosine 40, which is 192. Okay, now I need to get friction because friction's involved in my acceleration, in my down the incline direction. How am I going to do this? I'm going to say that friction is equal to mu n. So in this case, it's equal to, it's not less than, because this is going to be kinetic friction. So static friction, it could be less than or equal to. Kinetic is always just equal to. And so this is going to give me 0.25 times the normal force. And so my friction is 47.9. All right, now I can do my Fnet equals ma. And I'm going to take down the incline to be positive. So our rule is we take the direction of the acceleration to be positive. So I'm going to say down the incline is going to be my positive direction. So I'm going to have mg sine of 40 minus the friction is equal to ma. So A is going to be equal to mg sine of 40 minus the friction over that. So I'm going to plug in what I have. I'm going to have 25 times 10 times sine of 40 minus the 47.9 divided by the 25. And this gives me an acceleration that's 4.5 meters per second. Now, once I have the acceleration, I'm going to go back to the kinematics, and I'm going to say, okay, my initial velocity is 0, my acceleration is 4.5, my distance is 20. What is my time? And again, I'm going to use my x minus x naught. It's lucky for us that V naught is 0, so that cancels out, and I'm going to multiply by 2, divide by a, and square root. So I have 2 times 20 divided by 4, which gives us almost 3 seconds, 2.98 seconds. So that's as hard as it can get. Luckily for us in the lab, those inclines are nearly frictionless. All right, I'm going to clear the ink and move on to number 6. All right, an 18 kilogram block is on a flat frictionless table. It receives a force of 5 newtons to the right. What would be the block's acceleration? So we have a force pushing it to the right. I'm going to choose the right to be positive, because that's going to be my direction of acceleration. And so I have Fnet equals ma. I only have one force, so that is what's causing my acceleration. And then my acceleration is going to be this F push divided by m. So this is going to be 5 divided by 18, which is 0.28 meters per second. 7. A 25 kilogram block is on a rough surface. I believe this is supposed to be mu. Yeah, all of these Greek letters are shortcuts on Microsoft Word, and so they don't seem to keep it the same when they go from version to version and update the Microsoft Word itself. So my degree symbols and my mu symbols are constantly changing to different things. All right, so this is going to be more complicated. I'm going to have a push to the right. I'm going to have a weight going down. I'm going to have a normal going up, and I'm going to have a friction that is opposing the motion. So I want to get the friction first because I know I'll have to. So I'm going to say that Fnet is going to be equal to 0 in the y direction. It's not moving. So even though it's going this way, the normal and the weight are balanced. So I can do ups minus downs is equal to 0. So my normal is going to be equal to mg. And so this is going to be 25 kilograms, 10 meters per second, 250 newtons. And then again, friction is equal to mu n. So this is a good review of most of the stuff we've done so far this year. And I'm going to use my 0.4 and my 250, and that's going to give me 100 newtons. All right, so I'm going to pick the direction that it goes to be the positive direction, which happens to be the right in this case, but it could be left depending on how it is written for you. You can make that positive. And I'm going to say Fnet equals MA. So it's going to be F push minus friction is equal to MA, and F push minus friction over M. So my F push is 150. My friction was 100. My mass is 25. And so I have 50 divided by 25, which gives me 2. And again, starting from rest, how long would it take to travel 100 meters? And then what's my final velocity? So again, my initial velocity is 0. My acceleration is 2. My distance is 100 meters. And I want to know both my time and my velocity. So I would do x minus x naught equals v naught t plus 1/2 at squared. I would cancel out my v naught t. I would multiply by 2, divide by a, and square root. Whoa. So I have 2 times 100 divided by 2 meters per second squared. So 2 divided by 2 is 1. So square root of 100 is going to be plus or minus 10, but it's time, so it's going to be positive. It's 10 seconds. And then finally, my final velocity would be equal to v naught plus at, which this is 0. And my acceleration is 2. My time is 10. So it gives me a final velocity of 20.